Welcome to this video on Structural Analysis 2, where we will focus on influence lines for determinate beams, presented by M. Sudarsanan. Today, we are evaluating a train of 5 specific wheel loads crossing a simply supported beam with a total span of 22.5 meters. The loads are 120, 160, 400, 260, and 240 kN, separated uniformly by 2.5 meters intervals. Our objective is to calculate the maximum positive and negative shear forces at a given section. To do this efficiently, we will bypass tedious trial and error and use the shear increment method to pinpoint the exact critical load positions. To find the critical position for maximum positive shear force, we track the shear increment as the load train moves from right to left across section C. The total combined load of our train is 1,180 kilonewtons. First, we test moving the leading load, W1, to the left of our section. This yields a positive increment of plus 11.11, meaning the shear force is rising. Next, we test moving the second load, W2, to the left. This calculation results in a negative increment of minus 28.89. Because the shear increment changes sign from positive to negative, the maximum positive shear occurs precisely when W2 is positioned directly over section C. With our critical load position locked in, where the 160 kilonewtons load, W2, sits right over section C, we can construct our influence line diagram. Using the geometric properties of a simply supported beam, the baseline peak positive ordinate directly under W2 at the center section is 0.5. By applying linear interpolation across the remaining 2.5 meters load spacings, we determine the exact ordinates under every wheel load. The resulting values are minus 0.39 under W1, a positive 0.5 under W2, 0.39 under W3, 0.28 under W4, and 0.17 under W5. These ordinates represent the specific influence weight of each load. To compute the final maximum positive shear force, take the summation of each individual wheel load multiplied by its respective influence line ordinate results maximum positive shear force of 302.8 kilonewtons. Now let's pivot to finding the maximum negative shear force. The core principle remains identical, but our physical movement is reversed. We evaluate the shear increments by shifting our load system from left to right, intentionally keeping the bulk of our loads to the left of section C. When testing the movement of our trailing load, W5, across the section, our increment formula yields a value of minus 108.89. Because this shear increment value is immediately negative, it confirms that any further advancement would only reduce the negative effect. Therefore, the absolute worst-case negative shear scenario occurs when the fifth wheel load, W5, sits directly over section C. With W5 locked at section C, we construct our negative shear influence line diagram. The primary peak ordinate, directly under W5, is a clean minus 0.5. Working backward to the left along our train at our strict 2.5 meter spacing intervals, linear interpolation yields negative ordinates of minus 0.39 for W4, minus 0.2789 for W3, minus 0.167 for W2, and minus 0.056 for our first load, W1. Compiling the products of all 5 loads and their respective negative ordinates, our final mathematical calculation yields an absolute maximum negative shear force of minus 366.04 kilonewtons. Thank you for watching this video on calculating maximum positive and negative shear forces for determinate beams. We'll look on how to find absolute maximum bending moment for this same problem in the next video.